Hello and welcome back. In this video, we are going to combine two ideas that we learned earlier in the series, which is a feed-forward neural network and a recurrent neural network. And we'll try and combine these two into something that is called as a Hamming network. Hamming network. And probably wondering, Nilesh, why are we studying this network, given that I don't see it being used? Uh, so The reason is this is a original idea, and it's really interesting the way this network works. So hopefully, this this gives you an insight into how to think about building something that's totally unique. It could be very simple, but it does something specialized. So Hamming network has two parts to it, two layers. We start out with a um, input layer. So let's say this is our input layer, and as before we are going to call this as of size r. So r inputs p1 p2 p3 up to pr, and then we have the same boxes. So here what we get out of this is a um, input p, and that p is of shape r by 1, and that input goes into you already know that that goes into this box, which is the box for w, and then we also have a parallel box over here which is for b. So the box w, again this one has the shape of number of columns as number of rows in p, and then the number of neurons, which would be s in this case, and the bias b. Let's say that the bias has input of 1 that goes in, and the bias, each neuron has its own bias, so the shape of this would be s by 1. Then what we have is a point where we sort of bring these together, sort of summarize or sum them up, and for that what we are going to do is draw arrows to it. So this is going to be, so let me delete that. So we have w dotted with p that comes in here, and then b bias that comes in, and we add those two to then get us the net output n, and this output n would again have the shape is by one output per neuron. And after that what we do is take that input and pass it through a transfer function to get us the activations A. And so in this case, let's say the transfer function, especially in case of Hamming network, the transfer function used is the purelin. So we can draw that symbolically like this with a line going through, which simply is A has the values that n has. That's the purelin transfer function, which has s values in it, 1 per neuron. And then the output of this is A, which is the output of this layer, and it also has the shape of s by 1. Now this entire thing right here, up to here, this is called as the feed forward layer, meaning that the information flows from left to right in the forward direction only. After this, what we have is the second layer, and that second layer is the recurrent layer, and you may have already guessed how the recurrent layer is structured. The first thing that we need to know is there is a delay box. So let me draw one delay box right here. And so what happens is whatever input we have from this previous layer, output of previous layer becomes the input of this layer, and so when we bring that, we input that as an initial condition to this delay box, which we can write as D. Now, the delay box, as you may already know, has an output, and this output would be uh, the A at time t, right? A at time t, and this would have the same shape S by 1 as we had before. Now, what happens is in the delay block, uh, the values uh, are also sent back to the beginning of that recurrent network where it gets multiplied with the weights. And so if we draw the weights, let's say the weights could be here, and let's also draw in middle somewhere the activation or transfer function. So what we are going to see now is that this particular uh, value stored in the delay box gets sent back to the W right here, and this W again has values in it that will do a specific task, and I'll explain how that works with a concrete example. The output of this goes into this transfer function, and then the output of this goes back in the delay block. So point to note is that the delay block outputs value that was stored previously, does not output the value from the current iteration. And if you still have questions about how delay block works, I'd suggest looking at a previous video where we talk about the delay block. And in the recurrent layer, the transfer function used in case of the Hamming network is this one, which is a poslin transfer function, which is to say that if the values are negative, then the values are clipped to 0. If the values are positive, then they remain positive. Then those are kept. Now, once we are here, so this again has the shape S by S, because it will have as many neurons as uh, many values we had in the previous input, and then the n that is calculated is, here we say t plus 1 because this is not going to get output immediately. Therefore we are saying that this is sort of the future n that is calculated. It will be stored in the d and then will be output only in the next iteration. This again would have shape S by 1, so 1 output per neuron, and likewise we calculate the new values of A, and again t plus 1 because this is something that is going to be uh, output made available for output by the delay block in the next iteration only, and this will be the shape of S by 1. uh, this entire thing right here, that is the recurrent layer, and so to keep things symbolically clear, we are going to label superscript this A as A2, this A as A2, this N as N2, this W as W2, and that is because we are talking about layer 2. Likewise, we can label the A as with a superscript 1, N with a superscript 1, W with a superscript 1, and B with a superscript 1 because those are the values from the layer 1. And again, the A1 in this feed forward layer, the first layer, is uh, comes in from the purelin transfer function, purelin w dot p w1 dot p plus b1, and this is the exact same thing that we used to write previously, except that instead of writing s f, I'm using the name of the transfer function there. So that's the part one. And then for the second layer that we are using the poslin transfer function, and so we can write that out as well. So A20, so that's the initial condition, and that initial condition which would be somewhere here. This is the A0, and because this is layer 2, we put 2 there. That is simply the output of the previous layer, which is the activations of layer 1, A1. And then the A2, which A2 at time t plus 1, that is the new activations that are calculated, and again those are using the poslin transfer function, and it will be interesting to see how these transfer functions do something very special. W2 because this is the second layer, and we have a 2t instead of p because this is the output of this recurrent layer, which is the at so activations at time t, and 2 because it's the second layer. So this is sort of the structure of the Hamming. Now, before we move on to the actual example, a couple of things I need to point out that uh, are important and particular to the Hamming network. The W that we have here, this is sort of hard coded. The values of W do not change. So the W we it's like predetermined, and the values in it are written already like a template, and instead of W we call this as prototype. So the idea is that whatever input we get, let's say we have input of 1 2 3, let's say 1 2 3, uh, and then the W has the input of 1 2 3. Then you see that these sort of plays out really well. We get 1 plus 4 plus 9, and this gets us 14, a large value of the dot product. That tells us that the input is similar to the prototype, and that's a win. So that's what we are looking for. On the other hand, if we have the prototype, which is 1 2 3, but then the input that we have is, let's say, 1 0 0, then the values we get are 1 plus 0 plus 0, or maybe even minus 1. Then the output we get is minus 1. And so in this case, this input and the dot product is small. So as you can see, this is a smaller dot product, and this is not similar. So this is very dissimilar, and as compared to the other case, so not similar to the prototype that is there, and that so this is likely a mismatch with the this input is likely a mismatch with the prototype. That's the idea with this first layer with the W. And then when we uh, uh, get the dot product, input that to this recurrent layer, this W right here is also uh, sort of predetermined. So this W that we have is also predetermined. It's again hard coded, and it has a specific shape, as you'll see. So that W2 usually would be something like a diagonal of ones and some negative values along the uh, off diagonal places. What this does is, if we have uh, if we have some let's say we have 3 neurons in this first layer, and then we would have 3 rows, again 3 neurons in the second and recurrent layer, and so the W matrix would have 3 sort of rows, as we see here. and the input, that is the A that comes in, would also have 3 values. Let's say these values are something like 2, 2.1, 2.2, and so on. Then you'll see that when we multiply this with these values, in this case the very first value, which is so this is 3 by 3, and this is 3 by 1. So in the output we would expect something that is 3 by 1. So the first row here dotted with those values would give us what? It will give us 2 and some negative values here. So what we have is essentially one value is positive, which is because of this 1, and that is to say that that is the strength of that neuron which we are trying to increase, and the strength of other neurons we are trying to decrease. And this then is sort of amplified or worked on by this uh, poslin that we have here, this one. What this will do is it will clip the negative values. So if we were to write it out here, what we have is -2 for this is 2, then we have -2.1, and then we have -2.2. So what poslin would do is it will clip the negative values to 0, and it will just keep the 2 as is, and that would be the activation A. So in a sense, the recurrent layer, and it will do that over iterations. So until there is just one value in that vector that is positive, and the rest are 0. That's what I'm thinking. So the recurrent layer allows us to sort of extract pattern from a noise to identify something, and we'll see a bit more of this in the example right now. Now let's look at a concrete example, and here what we'll start out with is the very first layer, and what we will try and do is get our input. So the input, let's say the input is P, and we'll keep things simple. We shall just say that the input P has values 1, 1, 1, 1. So four values, and so the shape of this is simply 4 by 1. So that's the R we are talking about. And then comes the W. So the W is what we are going to do is W will say that it's hard coded, and so the values in it have already tried this, and these are the values: 0.75, 0.75, 0.75, and 0.75. That's the first row. Then we have 0.725, 0.725, and then 0.7725, again 0.725. And finally we have the third row, which is 0.7, 0.7, 7, then this is again 0.7, and this is again 0.7. So that is our uh, weight matrix, which is W1, and this is of the shape as we can see, 3 rows, so 3 by 4, 4 columns. And let's assume that B is simply 0. So when we now try to calculate the net input, that is the n value for n, we know that this we write is a n dot p plus b. We know that this is 0, so we can forget about b for now, and because this is layer 1, we are going to superscript this 1. So n1 then is equal to this above matrix W, and that is dotted with, so that's that matrix dotted with the values for P, which is 1, 1, 1. So essentially what this means is we are simply going to add all the values row wise. So for example, the first row is going to be 0.75 times 1 plus 0.75 times 1 plus 0.75 times 1 plus 0.75 times 1, and same thing for the second two rows. So in the end, what we would get is 0.75 added 4 times, so that's 3.0. This is 2.9 and 2.8. So that is the value we have for n1, and this is something that we would see right here. That's where we are. So that where we have the value of n1. Now we can keep going. So this value of n1 needs to go through the function, a transfer function, which is purelin. And what purelin says is that, well, a is equal to n with purelin, and so the value for a1 in this case is simply going to the values in n1, and that is equal to 3.0, 2.9, 2.8. And here we can see there is not really a clear distinction between the values in each of the rows, so they are pretty close. So hopefully the recurrent network would be able to find one value that is more similar or relevant, and the other two would be sort of minimized. And so once we have this, what we can do then is the second step, which is the recurrent layer. And in the recurrent layer, this a1 comes in as initial condition for a0, and so we have this 3.0, 2.9, 2.8 that is now input right here. That's where we are going to input that. And so let's keep going. The W2 again, in case of the recurrent layer, we are going to use some predetermined values, and the feature of that is that the diagonal has to be 1 and the off diagonal has to be negative. So we'll put 0 minus 0.5 in off diagonal places, and the diagonal values are all kept as 1. So with this, we then go ahead and try and calculate the value for n, and n, as before, this is going to be n2 at time t plus 1, and that is nothing but the w2 that we have dotted with p. Bias again is not there, so we'll just ignore that. And so what happens is we try and dot these values: 1 minus 0.5 minus 0.5, and that with 3.0, 2.9, 2.8, and so on. So this is minus 0.5, 1, minus 0.5, minus 0.5, 1, no, sorry, the minus 0.5 again, and then plus 1. So what we get in the end then is the following. We have 1 times 3.0 plus minus 0.5 times 2.9 plus plus minus 0.5 times 2.8, and so on for the other two rows. If we then try to calculate this in the calculator, so this is what we should see: 3.0 plus and then 0.5 times 2.9 gets us 1.45, and there's a negative sign with that, so I'm going to erase that plus sign there. That's going to be minus 1.45, and then again we have 0.5 times 2.8, that gets us minus 1.4, and again the same two rows would have the same value. Then we have 3.0 minus 1.45 minus 1.4, that gets us a value of 0.15, which is a positive value in this case. And if you go in and calculate the values for the remaining uh, rows here. This comes out to 0. So this comes out to 0 right here, and then this one comes out to minus 0.1. So let me write that clearly. So this comes out to 0, this comes out to minus 0.15. Now once we have these values, we can then put them through the transfer function. So a1 then would be poslin, the values for this, which is w2 times p, or w2, that's the same thing as saying poslin w2 a0, because that was the first iteration. So poslin, we have 0.15, 0 and minus 0.15, that's there. And what this outputs is, it clips the negative values at 0. So what we get in the output then is 0.15, 0 as 0, and then this minus 0.15 gets clipped to 0. So this becomes our a1, and so on go the iterations. In the following iteration, what we then do is try and calculate a2, which is simply w2 dotted with a1, and again w2 is the same that we had before, which is diagonal values are 1 1 1, these are minus 0.5, minus 0.5, minus 0.5, minus 0.5 off diagonal, and same thing here. And once we puff, and then a1 is this one, 0.1500. So once we complete this dotting, what we get in the output is, uh, and this has to, again this is n2, let me just write n2 because it has to go to poslin to get our value for a. So this could be n2, and this gets us value of 0.15 minus 0.075 minus 0.075, and for a2 then we need to put this through the poslin function, transfer function, and when we do that, what we poslin, we put these values 0.15 minus 0.075 minus 0.075, and as you would expect, all the negative values are clipped to 0. So what we get is 0.1500, and so what we can say that the final result that we have is uh, are these values for the activation. And in this case we can see that this is the value for neuron number 1, this is the value for neuron number 2, this is the value for neuron number 3, and among all of these 3 neurons we see that this neuron is a winner, uh, because it is the only neuron which is non-zero, and these are all zeroed out, and so those are not similar to the prototype. And so what we end up saying is that this particular uh, prototype 1, so what we say then is um, that the network picks prototype 1, prototype number 1 as the winner. That is the closest match to the input, and that's the whole story about the Hamming network, where we start out with a simple feed forward neural network, feed forward layer that calculates the with a fixed W, and then we put that through several iterations in the recurrent layer with a poslin that sort of zeroes out most of the outputs of neurons and keeps only one neuron that is non-zero, and then we say that, well, uh, that was the prototype which we have defined in here, where that input matches. So if it matches with prototype 1, we say that that's prototype 1. And to give you a sort of an idea is, let's say if we have image, so if we have 5 pixel by 5 pixel image of some digits, let's say 1 0 0 to 9 numbers, then uh, this particular R would be of shape, this would be of shape, if we unravel 5 by 5, we get 25 pixels in a row, right? 25 pixels in a row, and we can think of them as the input R. So this would be 25, and so our W here would be 25. And let's say we need one neuron per output, so we have 9 digits, 0 to 9. If we are trying to if we have, let's say, 100 images of digits, handwritten digits 0 to 9, we could have a prototype for each digit, and so we would have 10 such rows in this case. And so and again, then we would have some custom sort of weight matrix for the recurrent layer. And what that will do is, in the output, out of those 10 neurons, one for each digit, it will just have one neuron that is non-zero, and then we'll say, oh yes, the digit, the image that you had input uh, does match the prototype 8, which represents digit 8, and therefore that image must be digit 8. So that was my best effort to explain to you what Hamming network is. I hope you got the concept. If you have any questions, comments, or suggestions, please feel free to let me know in the comment section below. And again, what this learning this architecture of the Hamming network tells us is that something new. We are used to thinking that W needs to be optimized, but you could have the weight matrix W that already has a fixed predetermined template sort of values that can be used to directly match with the input and find the distance between those inputs and the values in the weight matrix or the prototype. And if the dot products happen to be larger, it means that those are similar, and that sort of reinforces the match that's in the input. All right, hope we continue this discussion in next videos. Please like, share, and subscribe. Thank you so much. Bye for now.